The last section of Chapter 9 deals with colligative properties. These are properties of solutions that depend only on the number of the dissolved particles in that solution, not the type of dissolved particles. And we're going to talk about 3 of these properties: freezing point depression, so the lowering of the freezing point, boiling point elevation or increasing boiling point, and osmotic pressure. We note the freezing point depression in the winter. I mean, we see it, but we don't think about why we do what we do in the winter. At least most people don't. But when we put salt on the roads, what's happening is that the salt is going to mix with the snow and form a solution, and it will cause the freezing point of water to lower. So the solution of the salt and water is going to freeze at a lower temperature than just pure water. Okay. When I just mentioned that when a substance is dissolved in water, then the freezing point of the water solution is lower than that of pure water. This is known as freezing point depression. And we can calculate that lowering of the temperature by this formula. So the change in temperature is given as Kf times m, where delta Tf is the number of degrees Celsius by which the freezing point is lowered. Now remember, to calculate the new freezing point, we would have to take the freezing point of pure water and subtract this delta T that we calculate. Kf is the freezing point depression constant for water, and it's given as 1.86 degrees Celsius per mol. And then m is the concentration of the solution expressed in molality. Here's a sample problem. We have ethylene glycol, which is an antifreeze in our automobiles. We'll calculate the freezing point of a solution that contains this many moles of ethylene glycol in this many grams of water. First, you will need to calculate the molality. We have moles of your solute, convert that to kilograms of water, and then use the formula in the previous slide using this value for the Kf and the value that you calculate for the molality to calculate the freezing point depression. So by how much do I lower the freezing point? And then subtract that from the freezing point of pure water to get the new freezing point of the solution. Boiling point elevation is the increase in boiling point. So when I dissolve a substance in water, that solution will boil at a higher temperature than pure water, which boils at 100 degrees Celsius. This is known as boiling point elevation. And the formula that we use to calculate that is pretty similar to the freezing point depression. So delta TB is equal to KB times M, where this delta T is the number of degrees by which the boiling point is raised. But remember, if I want to calculate the new boiling point, I would have to add the delta T to the original boiling point. In this case would be for water, which is 100 degrees. Kb is the boiling point elevation constant of water, which is 0.512 degrees Celsius per mol, and M is the concentration expressed in molality. Here's a sample problem. We have glycerol dissolved in water. Calculate the boiling point of a solution that contains 7.75 moles of glycerol in this much water, where the Kb for water is 0.52 degrees Celsius per mol. Remember to add the degrees elevated, so the delta T, to the boiling point of pure water to calculate the boiling point of the solution. Use this formula to calculate delta T, and then add that to the boiling point of pure water. Lastly, we'll talk about osmotic pressure. If I have an aqueous solution and pure water that I separated by a semi-permeable membrane is a membrane that allows only certain molecules to pass through, typically small molecules, but not larger ones. Then the water molecules will move through the membrane from the pure water to the solution, and this is called osmosis. The pressure that is necessary to stop this flow of water across the membrane is called the osmotic pressure of the solution. And obviously, the higher the solution concentration, the higher the osmotic pressure it will be, because those water molecules from the pure water are going to really want to go through the semi-permeable membrane into the concentrated solution side, and therefore the osmotic pressure needs to be higher to keep them from entering. Here's what an osmotic apparatus looks like. So if I have this side is the pure water and this side is the concentrated water, and they start at a certain height over here, and they're separated by this semi-permeable membrane, you can notice that it's mostly a size separation, so water can go through, but these larger molecules can't pass through here. And so what happens is when we allow them to equilibrate, what happens is that the level of the pure water will decrease, but the level of the concentrated side will increase. And that is because there's a flow of water from the pure side into and through the semi-permeable membrane into the concentrated side. This has an implication in biology, especially during red blood cells, and especially for those people who have to take IVs, for example. We have to make sure that we give them an isotonic solution, which means the iso means that the concentration of the outside solution and the concentration inside the cells is the same, and therefore there's not a movement of the water, a net movement, if you will, but the movement of water that goes out is the same as the one that the water that comes in, and so nothing happens to that red blood cell. What happens to the red blood cell when we have a hypotonic solution? That means that the concentration inside the cell is higher than the concentration outside the cell. You can think of it as that outside the cell being the pure water and the inside being the concentrated solution, and the cell membrane acts as that semi-permeable membrane from the U-shaped tube a couple of slides ago. The cell membrane can allow water to pass through, but acts as a barrier to larger molecules. Well, what happens when you have a solution that is lower in concentration than the inside of the cell is that water is going to flow in from outside inside, and then what happens is the red blood cell gets it enlarges, and it can blow up even because it gets filled with too much water inside. The opposite happens when we have a hypertonic, hyper meaning too concentrated. So outside it's much more concentrated than the inside of the cell. And think of it once again as the inside of the cell now is the pure water side, and the outside of the cell is the really concentrated solution. And what happens is that water leaves the cell and goes outside. And what happens to the cell is that it shrinks and it can even get destroyed. So these two examples, whether it's hypotonic or hypertonic, are not very good for the cell, but the isotonic solution is. And so it's very important when people come and they need IVs to give them the correct concentrations. Otherwise, their red blood cells will not withstand the solutions that are passing through the blood.